Introduction to renewable energy. Renewable energy systems harness natural resources that replenish themselves over relatively short timescales, offering a sustainable alternative to fossil fuels. These resources include sunlight, wind, water, geothermal heat, and biomass. The transition to renewable energy is crucial for mitigating climate change, reducing air pollution, and enhancing energy security. Understanding the fundamental principles behind these diverse energy sources is the first step towards developing and implementing effective sustainable solutions. This course will delve into each major renewable energy technology, examining its operational mechanisms and practical applications. The global demand for clean energy continues to grow, making expertise in this field increasingly valuable for future energy landscapes. Unlike finite fossil fuels, renewable sources provide a continuous supply of energy, making them inherently sustainable. Their widespread adoption can lead to significant environmental benefits, such as reduced greenhouse gas emissions and improved air quality. Furthermore, investing in renewable energy technologies stimulates economic growth, creates new jobs, and fosters technological innovation. This introductory section sets the stage for a deeper exploration into the specific technologies and their roles in a sustainable energy future. We will examine the historical context and the driving forces behind the current global shift towards these cleaner energy options. Why renewable energy matters. The urgency of transitioning to renewable energy stems from several critical global challenges, primarily climate change. Burning fossil fuels releases vast amounts of greenhouse gases, trapping heat in the atmosphere and leading to rising global temperatures, extreme weather events, and sea level rise. Renewable energy sources produce minimal to zero greenhouse gas emissions during operation, offering a direct solution to this environmental crisis. Beyond climate, reliance on fossil fuels creates geopolitical instability due to uneven distribution and price volatility. Diversifying energy sources with renewables enhances national energy independence and security, reducing vulnerability to global market fluctuations. This shift is not merely an environmental imperative, but also an economic and strategic necessity for a stable future. Pollution from fossil fuel combustion significantly impacts public health, contributing to respiratory illnesses and other chronic conditions. Renewable energy technologies, by contrast, produce little to no air or water pollution, leading to cleaner environments and healthier communities. Furthermore, the economic benefits are substantial, including job creation in manufacturing, installation, and maintenance sectors. Innovation in renewable technologies also drives down costs, making them increasingly competitive with traditional energy sources. Embracing renewables fosters a sustainable economy, protects natural ecosystems, and ensures a healthier planet for future generations, making their widespread adoption an undeniable priority for global well-being. Solar energy. Fundamentals. Solar energy is derived from the sun's radiation, which reaches Earth in the form of electromagnetic waves. This energy can be harnessed directly for electricity generation or heat production. The amount of solar radiation received at any given location depends on factors such as geographical latitude, time of day, season, and atmospheric conditions. Understanding these variables is crucial for optimizing the placement and efficiency of solar energy systems. The sun is an inexhaustible energy source, providing more energy in 1 hour than humanity consumes in an entire year. Capturing even a fraction of this abundant resource can significantly contribute to global energy needs. This fundamental principle underscores the immense potential of solar power as a primary renewable energy solution. The basic mechanisms for converting solar radiation into usable energy involve either photovoltaic (PV) technology or solar thermal technology. PV systems directly convert sunlight into electricity using semiconductor materials, while solar thermal systems capture solar heat for various applications, including water heating and electricity generation through steam turbines. Both methods rely on the sun's consistent energy output, though their conversion processes differ significantly. The efficiency of these systems is a key area of ongoing research and development, aiming to maximize energy capture and minimize material costs. Grasping these foundational concepts is essential for appreciating the diverse applications and future advancements in solar energy. Photovoltaic PV systems. Photovoltaic PV systems convert sunlight directly into electricity using the photovoltaic effect. This effect occurs when photons from sunlight strike a semiconductor material, typically silicon, dislodging electrons and creating an electric current. A single PV cell produces a small amount of power, so multiple cells are connected to form modules, commonly known as solar panels. These modules are then assembled into arrays to generate the desired power output for homes, businesses, or utility-scale power plants. The direct current, DC, electricity produced by PV panels is often converted into alternating current, AC, by an inverter for use in standard electrical grids and appliances. Understanding the components and their interaction is key to designing efficient PV systems. Key components of a typical PV system include solar panels, an inverter, mounting structures, and often a battery storage system. Solar panels capture sunlight. The inverter transforms DC into AC, and mounting structures secure the panels, usually at an optimal angle to maximize sun exposure. Battery storage systems are increasingly integrated to store excess electricity generated during peak sunlight hours for use when the sun is not shining, such as at night or on cloudy days. The efficiency of PV systems is measured by their ability to convert sunlight into electricity, with modern panels achieving significant conversion rates. Advances in materials science and manufacturing continue to improve PV system performance and reduce costs, making them a cornerstone of renewable energy. Solar thermal systems. Solar thermal systems harness the sun's energy to generate heat rather than electricity directly. These systems typically use collectors to absorb sunlight and convert it into thermal energy, which is then used for various heating applications. Common uses include domestic hot water heating, space heating for buildings, and even industrial process heat. The principle is straightforward. Dark-colored surfaces absorb more solar radiation, transferring as heat to a fluid, usually water or an antifreeze solution, circulating through the collector. This heated fluid then transfers its energy to a storage tank or directly to the application. Solar thermal technology is a highly efficient way to meet thermal energy demands. There are several types of solar thermal collectors, each suited for different applications and temperature requirements. Flat plate collectors are widely used for residential hot water, consisting of an insulated box with a dark absorber plate under a transparent cover. Evacuated tube collectors offer higher efficiency and can reach higher temperatures, making them suitable for commercial and industrial uses. Concentrating solar power, CSP systems, a more advanced form of solar thermal, use mirrors to focus sunlight onto a receiver, generating extremely high temperatures to produce steam for electricity generation. These diverse technologies demonstrate the versatility of solar thermal energy in meeting a wide range of heating needs, from low-temperature domestic uses to high-temperature power generation. Wind energy principles. Wind energy harnesses the kinetic energy of moving air to generate electricity. This kinetic energy is converted into mechanical energy by wind turbines, which then drive a generator to produce electrical power. The fundamental principle relies on the uneven heating of the Earth's surface by the sun, creating pressure differences in the atmosphere that result in wind. Wind turbines are designed to capture this airflow efficiently, with their blades acting like airplane wings to create lift and cause rotation. The amount of power a wind turbine can generate is primarily dependent on the wind speed, the swept area of its rotor, and the air density. Understanding these aerodynamic principles is essential for optimizing turbine design and placement. The power available in the wind increases significantly with wind speed, specifically with the cube of the wind speed. This means that even a small increase in wind speed can lead to a substantial increase in power output. Therefore, wind farms are typically located in areas with consistently strong winds, such as coastal regions, open plains, or offshore. Modern wind turbines are highly sophisticated machines, incorporating advanced aerodynamics, control systems, and materials to maximize energy capture and withstand various weather conditions. The continuous motion of air masses across the globe provides a vast, inexhaustible resource for clean electricity generation, making wind power a cornerstone of renewable energy portfolios worldwide. Types of wind turbines. Wind turbines are broadly categorized into two main types based on their axis of rotation: horizontal axis wind turbines, HAUTs, and vertical axis wind turbines, VOUTs. HAUTs are the most common design, featuring a rotor with 2 or 3 blades mounted on a horizontal shaft, similar to a propeller. These turbines typically face into the wind, often using a yaw mechanism to orient the rotor. TOTs are highly efficient and are used in both onshore and offshore wind farms, ranging in size from small residential units to massive utility-scale machines. Their widespread adoption is due to their proven efficiency and scalability in various wind conditions. Vertical axis wind turbines (VAWTs), while less common, offer distinct advantages, particularly in urban environments or areas with turbulent winds. Their main rotor shaft is set vertically, and the blades extend vertically from top to bottom. VAWTs do not need to be oriented into the wind, making them simpler in design and often quieter. Common VAWT designs include Darius and Savonius types. While generally less efficient than HAWTs for large-scale power generation, VAWTs can operate effectively in lower wind speeds and have a smaller footprint. Both HAWTs and VAWTs continue to evolve, with ongoing research focused on improving efficiency, reducing noise, and enhancing durability for diverse applications. Wind farm development. Developing a wind farm is a complex multi-stage process, beginning with site selection. This involves extensive assessment of wind resources, topography, environmental impact, and proximity to transmission lines. Detailed wind mapping and meteorological studies are conducted to identify locations with optimal and consistent wind speeds. Environmental impact assessments, EIAs, are crucial to evaluate potential effects on wildlife, particularly birds and bats, as well as noise impacts on nearby communities. Permitting and regulatory approvals follow, often involving local, regional, and national authorities. This initial planning phase is critical for the long-term success and sustainability of the project, ensuring compliance and minimizing adverse effects. Once a suitable site is identified and approved, the development proceeds to financing, engineering design, procurement, and construction. Securing financing from investors and lenders is a significant hurdle, requiring robust economic models and risk assessments. Engineering design involves optimizing turbine layout, foundation design, and electrical infrastructure. Procurement of turbines, towers, and other components follows, often from global manufacturers. The construction phase includes building access roads, foundations, erecting turbines, and installing electrical cabling and substations. Finally, the wind farm undergoes commissioning and testing before becoming fully operational. Ongoing operations and maintenance, O&M, are then critical for maximizing energy output and ensuring the longevity of the assets, making wind farm development a long-term commitment. Hydropower. Basics. Hydropower harnesses the energy of moving water to generate electricity, making it one of the oldest and most established forms of renewable energy. The fundamental principle involves converting the kinetic energy of flowing water into mechanical energy, which then drives a turbine connected to an electrical generator. Most hydropower plants utilize dams to create a reservoir, storing water at a higher elevation. When water is released from the reservoir, it flows through large pipes called penstocks, turning the blades of a turbine. The greater the height difference, head, and the volume of water, the more electricity can be generated. This reliable and dispatchable power source plays a significant role in global energy grids. Hydropower systems are generally classified by their generating capacity and the way they manage water flow. Large-scale conventional hydropower plants, often associated with large dams, provide significant baseload power and can respond quickly to changes in electricity demand. Run-of-river hydropower systems, by contrast, divert a portion of a river's flow through a powerhouse without creating a large reservoir, minimizing environmental impact. Pumped storage hydropower is another important type, where water is pumped to an upper reservoir during periods of low electricity demand and released to generate power during peak demand, essentially acting as a large-scale energy storage solution. Each type offers distinct advantages and applications, contributing to a diverse renewable energy portfolio. Small-scale hydropower, often referred to as mini-hydro, micro-hydro, or pico-hydro, refers to systems with generating capacities typically below 10 megawatts MW. These systems are particularly valuable for providing decentralized electricity to remote communities or off-grid locations where connecting to a national grid is impractical or too costly. Unlike large dams, small-scale hydro projects usually have minimal environmental impact, often utilizing existing natural water flows without the need for large reservoirs. They can be designed as run-of-river systems, which divert a portion of a stream through a turbine and return it to the river downstream. This approach preserves the natural flow and ecosystem of the river. The advantages of small-scale hydropower include low operating costs, long lifespan, and a reliable, continuous power supply. These systems are often community-owned and managed, empowering local populations with access to clean energy and fostering economic development. Pico-hydro systems, generating less than 5 kilowatts, are simple enough for individual households or small clusters of homes. Micro-hydro systems, up to 100 kilowatts, can power villages, while mini-hydro up to 1 megawatt and small hydro up to 10 megawatts can serve larger communities or small industrial needs. The modular nature and adaptability of small-scale hydropower make it an excellent solution for sustainable rural electrification and localized energy independence, contributing significantly to energy access goals worldwide. Geothermal energy sources. Geothermal energy originates from the heat within the Earth's core, a vast and continuous source of thermal energy. This heat is generated by the slow decay of radioactive isotopes in the Earth's mantle and crust, and residual heat from the planet's formation. Geothermal resources are found worldwide, but are most accessible in regions with active volcanic activity or tectonic plate boundaries, where hot magma is closer to the surface. These areas often feature hot springs, geysers, and fumaroles, which are natural manifestations of the Earth's internal heat. Harnessing this energy involves tapping into underground reservoirs of hot water or steam. Understanding the geological conditions is crucial for identifying viable geothermal sites. There are several types of geothermal resources, each with different characteristics and applications. Hydrothermal resources, the most common type used for electricity generation, involve reservoirs of hot water and steam trapped in fractured rock formations. These are typically found at depths of a few kilometers. Enhanced geothermal systems, EGS, aim to create or improve hydrothermal reservoirs in areas where natural permeability or fluid content is insufficient. This involves injecting water into hot, dry rock to create artificial fractures and circulate water for heating. Direct use applications, such as district heating and agricultural uses, tap into lower temperature geothermal waters. The versatility of geothermal energy, from direct heat to electricity, makes it a valuable and reliable renewable resource, offering continuous power independent of weather conditions. Geothermal power plants. Geothermal power plants convert the Earth's internal heat into electricity, typically by using steam to drive turbines. There are three primary types of geothermal power plants: dry steam, flash steam, and binary cycle. Dry steam plants, the simplest and oldest design, directly use steam from the geothermal reservoir to turn a turbine. Flash steam plants, the most common type, extract high-pressure hot water from the earth, which flashes into steam as its pressure drops, driving a turbine. Both dry and flash steam plants release some steam into the atmosphere, though modern designs often re-inject condensed water back into the reservoir. Understanding these different approaches is crucial for selecting the appropriate technology for a given geothermal resource. Binary cycle power plants are a more recent development and can operate with lower temperature geothermal fluids. Instead of directly using steam or hot water, these plants use the geothermal fluid to heat a secondary working fluid, such as isobutane or pentane, which has a much lower boiling point. This secondary fluid then vaporizes, driving a turbine to generate electricity. The geothermal fluid is never exposed to the atmosphere and is re-injected back into the earth, making binary cycle plants a closed-loop system with minimal environmental impact. This technology expands the range of viable geothermal resources, allowing for power generation in areas without high-temperature steam. The continuous operation of geothermal plants provides reliable baseload power, making them a valuable asset in a diversified renewable energy grid. Biomass energy conversion. Biomass energy is derived from organic matter, including plants, agricultural waste, animal waste, and municipal solid waste. This organic material stores solar energy through photosynthesis, which can then be released as heat or converted into electricity or biofuels. Biomass is considered a renewable resource because new organic matter can be grown or replenished continuously. The conversion of biomass into energy can occur through various processes: direct combustion, gasification, pyrolysis, and anaerobic digestion. Each method is suited for different types of biomass and desired energy outputs. Understanding these conversion pathways is essential for maximizing the energy potential of diverse biomass feedstocks. Direct combustion involves burning biomass directly to produce heat, which can then be used for space heating, industrial processes, or to generate steam for electricity production. Gasification converts biomass into a combustible gas mixture called syngas, which can be used in engines or turbines. Pyrolysis, a thermal decomposition process in the absence of oxygen, produces bio-oil, biochar, and syngas. Anaerobic digestion, a biological process, breaks down organic matter in the absence of oxygen to produce biogas, primarily methane, which can be used for heat or electricity. The choice of conversion technology depends on factors such as the type and availability of biomass, the desired end product, and economic considerations. Sustainable sourcing of biomass is crucial to ensure its environmental benefits are realized. Biofuels and biogas. Biofuels are liquid or gaseous fuels derived from biomass, serving as renewable alternatives to fossil fuels in transportation and other sectors. The most common biofuels are ethanol and biodiesel. Ethanol is typically produced from crops rich in sugar or starch, such as corn, sugarcane, or cellulosic biomass, through fermentation. Biodiesel is made from vegetable oils, animal fats, or recycled cooking grease through a chemical process called transesterification. These fuels can be used in existing engines, often in blends with petroleum fuels, reducing greenhouse gas emissions and reliance on imported oil. The development of advanced biofuels from non-food sources is a key area of research to address concerns about food security. Biogas is a gaseous fuel produced from the anaerobic digestion of organic matter, primarily composed of methane, 50 to 75%, and carbon dioxide. Common feedstocks for biogas production include animal manure, sewage sludge, agricultural residues, and organic municipal waste. Biogas can be directly combusted for heat and electricity generation, or it can be upgraded to biomethane, renewable natural gas, by removing impurities and carbon dioxide. Biomethane is chemically identical to natural gas and can be injected into existing gas pipelines or used as a vehicle fuel. Both biofuels and biogas offer versatile solutions for decarbonizing transportation, heating, and electricity sectors, providing dispatchable renewable energy and contributing to waste management. Their sustainable production is vital for their long-term environmental benefits. Ocean energy technologies. Ocean energy encompasses a variety of technologies that harness the vast power contained within the world's oceans. These include tidal energy, wave energy, ocean thermal energy conversion (OTEC), and salinity gradient power. The oceans represent an immense, largely untapped renewable energy resource, offering consistent and predictable energy flows. Tidal energy utilizes the gravitational forces of the moon and sun, creating predictable high and low tides. Wave energy captures the kinetic energy of surface waves generated by wind. OTEC exploits the temperature difference between warm surface water and cold deep water. Salinity gradient power harnesses the energy released when fresh water and salt water mix. Each technology presents unique engineering challenges and opportunities for clean energy generation. While still in earlier stages of commercial development compared to solar and wind, ocean energy technologies hold significant promise for future energy security. Tidal barrages and tidal stream generators are the most mature forms of tidal power, with several operational plants worldwide. Wave energy converters come in various designs, including buoys, oscillating water columns, and overtopping devices, each with different mechanisms for capturing wave motion. GoTech and salinity gradient technologies are less developed, but offer potential for baseload power in specific geographical locations. Research and development efforts are focused on improving efficiency, reducing costs, and ensuring environmental compatibility. The predictability and high energy density of ocean resources make them an attractive long-term solution for renewable energy supply, especially for coastal regions and island nations. Tidal and wave power. Tidal power harnesses the energy of the ocean's tides, which are caused by the gravitational pull of the moon and sun. Tides are highly predictable, making tidal energy a reliable and consistent source of electricity. There are two main types of tidal power technologies: tidal barrages and tidal stream generators. Tidal barrages are essentially dams built across estuaries or bays, creating a basin. As the tide comes in, water flows into the basin, and as it goes out, the trapped water is released through turbines to generate power. This method is similar to conventional hydropower, but uses tidal cycles instead of river flow. Tidal barrages can generate significant amounts of power, but have a substantial environmental footprint. Tidal stream generators, by contrast, are more akin to underwater wind turbines. They capture the kinetic energy of tidal currents without the need for a barrage. These devices are typically placed in areas with strong tidal flows, such as narrow channels or straits. They have a smaller environmental impact than barrages and can be deployed in a more modular fashion. Wave power, on the other hand, captures the energy from ocean surface waves. Various technologies exist, including oscillating water columns, OWCs, point absorbers, buoys, and overtopping devices. OWCs trap air above the water column, which is then compressed and decompressed by wave action, driving an air turbine. Point absorbers float on the surface, converting vertical motion into electricity. Overtopping devices capture waves in a reservoir at a higher elevation, then release the water through a turbine. Both tidal and wave power offer immense potential for clean, predictable energy, though technological and economic challenges remain. Energy storage solutions. Energy storage solutions are critical for integrating intermittent renewable energy sources like solar and wind into the electrical grid. Renewables often produce electricity when it's not immediately needed, or not enough when demand is high, leading to imbalances. Storage technologies allow excess energy to be captured and held for later use, improving grid stability, reliability, and efficiency. This enables a higher penetration of renewables by ensuring a continuous and dispatchable power supply. Without effective storage, the variability of solar and wind power can pose significant operational challenges for grid operators. Therefore, advancements in energy storage are paramount for a successful transition to a fully renewable energy system. A diverse range of technologies exists for energy storage, each with different capacities, durations, and costs. These include batteries, lithium-ion, flow batteries, lead-acid for short to medium duration storage, pumped hydro storage, which uses gravitational potential energy for large-scale, long-duration storage, compressed air energy storage, CAES, and liquid air energy storage, LAES, for medium to long-duration storage, thermal energy storage, which stores heat or cold for later use, flywheels for very short duration, high-power applications. The selection of an appropriate storage technology depends on the specific application, required storage duration, power capacity, and economic viability. Continued research and development are driving down costs and improving the performance of these essential technologies. Battery storage technologies. Battery storage technologies are rapidly advancing, becoming a cornerstone of modern renewable energy systems due to their versatility and decreasing costs. Batteries store electrical energy chemically and release it as needed. Lithium-ion batteries are currently the most prevalent technology for grid-scale and residential applications, offering high energy density and efficiency. However, other battery chemistries are also important, including lead-acid batteries for cost-effective, shorter duration storage, and nickel-cadmium batteries for specific industrial uses. The performance of a battery is characterized by its capacity, how much energy it can store, power, how quickly it can deliver energy, cycle life, how many charge-discharge cycles it can endure, and efficiency. Understanding these metrics is vital for selecting the right battery for a given application. Beyond lithium-ion, emerging battery technologies like flow batteries and solid-state batteries are gaining traction. Flow batteries store energy in liquid electrolyte solutions, offering distinct advantages for long-duration storage due to their scalability and ability to separate power and energy components. Solid-state batteries, still largely in the research and development phase, promise higher energy density, improved safety, and longer lifespan compared to conventional lithium-ion batteries. The continuous innovation in battery chemistry and manufacturing processes is driving down costs and improving performance, making battery storage increasingly competitive. These advancements are crucial for enabling a higher penetration of intermittent renewables, providing grid services, and supporting electric vehicle adoption, fundamentally transforming the energy landscape. Grid integration of renewables. Integrating renewable energy sources into existing electrical grids presents both opportunities and challenges. The primary opportunity is the decarbonization of electricity generation, leading to significant environmental benefits. However, the intermittent nature of many renewables, particularly solar and wind, requires careful management to maintain grid stability and reliability. Traditional grids were designed for centralized, dispatchable power plants, making the integration of distributed and variable renewable sources complex. Challenges include managing voltage fluctuations, frequency deviations, and ensuring adequate reserve capacity. Effective grid integration strategies are essential to maximize the benefits of renewables while minimizing disruptions to power supply. This requires advanced planning and technological solutions. Key strategies for successful grid integration include forecasting, accurate prediction of renewable energy output, solar irradiance, wind speed, and electricity demand. Energy storage. Deploying battery storage, pumped hydro, or other storage solutions to balance supply and demand. Grid modernization. Upgrading transmission and distribution infrastructure to handle bidirectional power flow and variable generation. Demand-side management. Encouraging consumers to shift electricity consumption to align with renewable energy availability. Smart grid technologies. Implementing advanced sensors, communication, and control systems for real-time grid management. These strategies work in concert to create a more flexible, resilient, and intelligent grid capable of accommodating a high penetration of renewable energy. The goal is to evolve from a reactive grid to a proactive, self-healing system that can seamlessly integrate diverse energy sources. Smart grids and renewables. Smart grids represent the next generation of electrical power systems, integrating advanced digital technologies with the existing grid infrastructure. These intelligent grids are designed to enhance reliability, efficiency, and sustainability, particularly in accommodating a high penetration of renewable energy. Key features of a smart grid include two-way communication between utilities and consumers, real-time monitoring and control capabilities, and automated responses to disturbances. This advanced infrastructure allows for dynamic management of electricity flow, enabling better integration of distributed renewable generation and demand-side management. The transition to smart grids is fundamental for unlocking the full potential of renewable energy sources and building a resilient, future-proof energy system. The benefits of smart grids for renewable energy integration are numerous. They enable improved grid stability by quickly detecting and responding to fluctuations from intermittent renewables, enhanced efficiency through optimized power flow and reduced transmission losses, greater consumer participation through smart meters and demand response programs, allowing users to manage their energy consumption more effectively, facilitation of distributed energy resources, DERs, such as rooftop solar and electric vehicle charging, by managing their impact on the local grid, increased resilience against outages through self-healing capabilities and rapid fault detection. By leveraging data analytics, artificial intelligence, and advanced control systems, smart grids transform the energy landscape, making it more flexible, responsive, and sustainable. They are an indispensable component of a future powered predominantly by renewable energy. Energy efficiency measures. Energy efficiency refers to using less energy to achieve the same or better level of service, comfort, or output. It is often considered the first fuel in the transition to a sustainable energy system, as reducing demand lessens the need for new energy generation, including renewables. Implementing energy efficiency measures is typically the most cost-effective way to reduce greenhouse gas emissions and lower energy bills. These measures span across all sectors: residential, commercial, industrial, and transportation. From improving building insulation to optimizing industrial processes, efficiency plays a crucial role in minimizing overall energy consumption. Prioritizing efficiency ensures that renewable energy systems can meet actual demand more effectively and sustainably. Common energy efficiency measures include building insulation and weatherization to reduce heating and cooling loads, high-efficiency appliances and lighting, example LED lights, that consume less electricity, smart thermostats and energy management systems to optimize energy use in buildings, industrial process optimization, such as waste heat recovery and motor upgrades, efficient transportation options, including electric vehicles and public transit, reducing fuel consumption. Behavioral changes like turning off lights and unplugging electronics also contribute significantly. By systematically implementing these measures, societies can dramatically reduce their energy footprint, making the transition to renewable energy both more feasible and more impactful. Energy efficiency is a foundational pillar of any comprehensive sustainable energy strategy, complementing renewable energy generation. Policy and regulatory frameworks. Effective policy and regulatory frameworks are essential drivers for the widespread adoption and development of renewable energy systems. Governments play a crucial role in creating a stable and supportive environment for renewable energy investments. Policies can include financial incentives such as tax credits, grants, and feed-in tariffs, which guarantee a fixed price for renewable electricity fed into the grid. Renewable Portfolio Standards, RPS or quotas, mandate that a certain percentage of electricity must come from renewable sources, creating market demand. These policies help overcome initial cost barriers and reduce investment risks, accelerating the deployment of clean energy technologies. A clear and consistent policy landscape provides certainty for developers and investors, fostering growth in the sector. Beyond financial incentives, regulatory frameworks address issues such as grid access, permitting processes, and environmental standards. Streamlined permitting procedures can significantly reduce project development timelines and costs. Grid connection rules ensure fair access for renewable generators to the transmission and distribution networks. Environmental regulations ensure that renewable energy projects are developed responsibly, minimizing their impact on ecosystems and local communities. International agreements and carbon pricing mechanisms further incentivize the transition away from fossil fuels. The interplay of these policies and regulations at local, national, and international levels shapes the pace and direction of renewable energy deployment, making them indispensable tools for achieving climate and energy goals. Continuous adaptation of these frameworks is necessary to keep pace with technological advancements and market dynamics. Economic aspects of renewables. The economic landscape of renewable energy has transformed dramatically over the past decade, with costs for technologies like solar PV and wind power falling significantly. This cost reduction, driven by technological advancements, economies of scale, and supportive policies, has made renewables increasingly competitive with, and often cheaper than, new fossil fuel power generation. The levelized cost of electricity, LCOE, which measures the lifetime cost of building and operating a power plant divided by its lifetime energy output, consistently shows renewables as the most affordable new energy sources in many regions. This economic competitiveness is a powerful driver for global adoption, moving renewables beyond niche markets into mainstream energy supply. Understanding these economic trends is crucial for investment decisions and policy planning. Beyond direct generation costs, renewable energy offers broader economic benefits. These include job creation. The renewable energy sector is a significant source of employment in manufacturing, installation, operations, and maintenance. Energy security. Reducing reliance on volatile fossil fuel markets leads to more stable energy prices and national energy independence. Local economic development. Renewable projects often bring investment and tax revenue to rural communities. Reduced environmental and health costs. Avoiding pollution from fossil fuels saves billions in healthcare and environmental remediation. Innovation and technological leadership. Investment in renewables fosters research and development, creating new industries and export opportunities. The long-term economic advantages, coupled with environmental imperatives, position renewable energy as a cornerstone of sustainable economic growth and a resilient future. Environmental impacts and benefits. Renewable energy systems offer substantial environmental benefits, primarily by reducing greenhouse gas emissions and air pollution compared to fossil fuels. This directly combats climate change and improves public health. However, like any energy technology, renewables also have environmental impacts that must be carefully managed. For example, large-scale solar farms require significant land area, potentially impacting ecosystems and land use. Wind farms can affect bird and bat populations, and their visual and noise impacts are sometimes a concern for local communities. Hydropower dams can alter river ecosystems, fish migration, and sediment flow. Understanding and mitigating these impacts is crucial for truly sustainable development. Environmental impact assessments, EIAs, are standard practice to identify and address these concerns. Despite these localized impacts, the overall environmental benefits of renewable energy far outweigh those of fossil fuels. The life cycle greenhouse gas emissions of renewables, from manufacturing to operation, are significantly lower. Furthermore, renewables reduce dependence on mining and drilling for fossil fuels, which often have destructive environmental consequences. Mitigation strategies for renewable projects include careful site selection to avoid sensitive habitats, implementing bird and bat deterrent systems for wind turbines, designing fish ladders and minimum flow requirements for hydropower, recycling and responsible disposal of components at end of life. By continuously improving technology and implementing best practices, the environmental footprint of renewable energy can be minimized, ensuring their vital role in a clean, sustainable future. A net effect is overwhelmingly positive for the planet. Future trends in renewables. The renewable energy sector is characterized by rapid innovation and evolving trends that promise to further accelerate the global energy transition. One major trend is the continued decrease in costs for solar PV and wind power, making them the cheapest forms of new electricity generation in many parts of the world. This trend is expected to continue, driving even wider adoption. Another significant development is the increasing focus on energy storage, particularly advanced battery technologies, which are crucial for overcoming the intermittency of renewables and enhancing grid stability. We are also seeing a shift towards hybridization, combining different renewable sources, e.g., solar and wind, with storage to create more reliable and dispatchable power plants. These trends are reshaping the energy landscape and accelerating the move away from fossil fuels. Further future trends include decentralization and distributed generation, more energy production occurring closer to consumption, such as rooftop solar and community microgrids, digitalization and AI, leveraging artificial intelligence, machine learning, and big data for optimized forecasting, grid management, and predictive maintenance. Green hydrogen, production of hydrogen using renewable electricity, offering a pathway to decarbonize hard-to-abate sectors like heavy industry and long-haul transport. Advanced materials, development of more efficient, durable, and sustainable materials for solar cells, wind turbine blades, and batteries. Circular economy principles, focusing on recycling and reuse of renewable energy components to minimize waste. These emerging trends indicate a future energy system that is not only clean, but also highly intelligent, resilient, and integrated, providing sustainable energy solutions for a growing global population. Career opportunities in renewables. The renewable energy sector is experiencing rapid growth globally, creating a diverse array of career opportunities across various disciplines. This expansion is driven by increasing investment, technological advancements, and supportive government policies. From engineering and project management to finance, policy, and skilled trades, there is a growing demand for professionals with expertise in renewable energy systems. The sector offers stable, long-term employment prospects as the world transitions towards a sustainable energy future. Understanding the breadth of these opportunities is crucial for individuals considering a career in this dynamic field. Many roles require interdisciplinary skills, combining technical knowledge with business acumen and environmental awareness. Specific career paths in renewable energy include renewable energy engineer, designing, developing, and optimizing solar, wind, hydro, or geothermal systems. Project manager, overseeing the planning, execution, and completion of renewable energy projects. Installation technician, installing, maintaining, and repairing solar panels, wind turbines, and other equipment. Environmental consultant, conducting impact assessments and ensuring regulatory compliance for projects. Energy analyst, evaluating market trends, policy impacts, and economic viability of renewable projects. Research and development scientist, innovating new materials, technologies, and efficiency improvements. Additionally, roles in sales, marketing, finance, and policy advocacy are vital for the sector's continued growth. Continuous learning and specialization in specific renewable technologies or aspects like energy storage and grid integration can further enhance career prospects in this exciting and impactful industry.